even better depiction of kind of how this C. hairy expression changes. So this is the embryo at the beginning time, time 0, and then this is 18 hours. And so there is a very predictable kind of every 1.5 hours you get the formation of a new somite block. Okay? And each of these somite formation events coincides with an activation and then inactivation of Notch signaling. Okay, so the Notch signaling pathway is probably one of the most simplest in terms of its intracellular events. So basically you have the Notch receptor. It binds to its ligand. We'll talk about some called delta ligands. And when the receptor binds to its ligand, the intracellular portion of this receptor gets cleaved. And when it gets cleaved, this intracellular portion can be activated to migrate into the nucleus, where it acts as an activating co-activator of gene transcription. So some of the Notch signaling genes include C. hairy1, which is what I just showed you. These other genes called lunatic fringe, HES1, A1, Notch is the receptor, and delta is the ligand. Okay, so the link between the production of each somite and Notch signaling has been made because when you mutate different genes in the Notch signaling pathway, for example in mice, you get phenotypes that show mutations in vertebrate segmentation and vertebrae semenogenesis. Okay, so this is another signaling pathway gene showing you a little bit more complexity. So this is the Notch receptor. In the mouse, there's actually 4 different types, so there's Notch 1 to 4. And these are the ligands. Delta, so DLL1. So there's delta 1, delta 3, delta 4. Inside the cell that, this is ICN, is the intracellular portion of Notch that goes to the nucleus. And lunatic fringe is a gene that is thought to help in increasing the affinity of Notch for its ligands. Okay, so this is just a diagram. If you're interested to kind of show you the complexity of this signaling, relatively simple signaling pathway. And if you're interested, you can look at this review article for more kind of information on how the vertebrate's segmentation occurs and how Notch is involved. Okay, but like I said, there's severe phenotypes that you see in mice that have mutations in Notch signaling partners. Okay, so here on the left is basically X-ray or staining for skeletal bone in a normal mouse. And here you see marked by these squares different individual vertebrae. And so this is more the cervical, and then you have 5 individual thoracic vertebrae. In a mouse that has a mutation in delta 3, which is a ligand for Notch signaling, you see a very severe defect in the development of the vertebrae in this mouse. So here, the vertebrae at the thoracic end are somewhat fused. So instead of having 5 in a row, there's kind of 5 kind of fused together. And you get somewhat of duplications of the cervical vertebrae. Okay, and just to kind of illustrate what this mouse looks like, it's been nicknamed the pudgy mouse because compared to our normal mouse, I've worked with these mice. They're like super small, Like there, I can even draw you what it looks like, because it's kind of, I was amazed. Okay, so if you see, if this is your mouse, okay, this is the wild type, right, has a tail, it's its full length, okay. The Delta 3 mouse is more like this, okay. It's really small, okay. And it doesn't have a tail. It's got like a little nub. Makes it very difficult to pick up.
So they live?
They live and they can breed, but they're not very motile because their vertebrae are fused. Yeah, so this is a one of the rare occasions where a mutation in Notch signaling doesn't kill the embryo early on. So Delta 3 is kind of a unique mouse, and it was first discovered because of this drastic phenotype. So it demonstrates again how Notch signaling affects anterior to posterior identification and development. And Notch signaling in zebrafish also has been shown to play a role. That's so funny.
We both said, I want one at the exact same time.
You can get them. I'm trying to think, you could probably order one. I don't know how long you.
I don't think my cats would be good.
You might be scared.
No, they might.
I'll try to find an actual photo of one. Okay, so going back to, this is our zebrafish embryo. In the zebrafish, the Notch signaling genes that are activated are HER1 and HEY. And this is a in situ. Is it in situ? Yeah. Okay. This is in situ for these genes. So you can see the red is the HER1 here, and then in the somites, K1 is expressed in each of those developing somites. And then this is the yolk. So, so if you look at, or if you watch a time-lapse video of somite formation in the zebrafish, so if you mark here with the asterisk, the original kind of just to orient you where you are at, and then wait for the formation of the next somite. The expression of HEY1 is kind of, it's not present, and then it's not present in the in this region here, and then as the somite forms, it becomes more evident as the vertebrae are forming and the embryo is elongating. So I forget what this movie is. So this movie shows real-time images of the pre-Semitic mesoderm of expression of HES1 involved in Notch signaling during somite formation. Okay, so you see how that wave of expression is occurring? That is HES1, its expression being activated as each somite is formed. So it's on here in this somite, more anterior. And then, see, the somites were formed and they moved down. And so the notch is being activated in the individual somite as it's being formed. It's like a pattern oscillation, on, off, on, off.